All right, so CDMA stands for Code Division Multiple Access. So it's a form of multiplexing. We have frequency multiplexing, and we have time division, frequency division multiplexing, time division multiplexing, right? So division multiplexing is another technique in order to allow users to share the same medium, okay? All right. So before we go into CDMA, let's review something called amplitude modulation. All right. So just write a just say yes or no in the chat window. Have you learned about amplitude modulation before? I assume that engineering students must have learned this before. All right, so 2 people say yes. If you haven't learned, just say no as well. That's fine. All right, so I assume that many students have learned about amplitude modulation. So basically, this is a modulation technique that radio stations use to broadcast their signal. So basically, the original message is this. So you can imagine this as a song, for example. And each radio station is given a specific frequency. And their frequencies must be separated from each other to avoid interference, right? So in that case, we call them orthogonal frequencies. When we say orthogonal, means that they do not overlap. So that's why they do not interfere with each other. So because of that, you can have many radio stations in the same city because each has its own frequency. So to transmit or to broadcast their radio, they would use something called a carrier, and that is the frequency given to them by the government. And then they would modulate the original signal using the carrier, right? And this is the resulting signal. And this signal is broadcast. And then if you are in a car and you turn on the radio, if you don't use satellite, if you use the regular radio service, this is the signal that the radio in your car gets, and it will translate this into demodulate the signal, and then it will give you the original message or the original song, right? So CDMA uses a similar concept, but with digital signal, all right? So you see these are analog signals. Now CDMA uses similar concept, but uses digital signal, okay? So just a question, have you learned about CDMA before? So again, please type in the chat window, yes or no. CDMA, have you learned this CDMA before in other courses? All right, so one student say yes. Okay. All right, one person say yes. Okay, so one person did but forgot. Okay. All right. Okay, so one student say no, doesn't ring a bell. Okay, so probably not. All right, so we can start from the beginning as if no one had learned about CDMA. All right. So CDMA. So it's a multiplexing technique used with spread spectrum, right? So we're not going to learn about spread spectrum in detail in this course, but the main idea is given a data signal of rate D, right? Let's say D bits per second, all right? So again, this works with digital signal, D bits per second. And then we break each bit into K chips, or it means K smaller bits, all right? K smaller bits according to a fixed chip encode given to a specific user. So because now for every bit, we break it into K smaller bits, the new data rate is K times D, right? So for example, if D is, let's say 1 kilobits per second. And then you break each bit in this stream into, let's say, 8 smaller bits. So now the new data rate would be 8 bits per second, right? So that's the main idea. So this is an illustration, all right? Okay, all right, so in this example, this is the original data. So let's say this is 1010, right? 1010. This is the sequence of binary digits, 1010. And this is the chips that we've talked about before, all right? So in this example, there are 10 chips, all right? 10 smaller bits, because we count, let's say from here to here, you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? So basically for every original data bit, you encode it using 10 smaller bits, all right? 10 smaller bits. So K is 10 in this case, right? So if we use this example, so K could be 10 in this case. And this pattern is repeated. So you can see it starts with this and then a longer one. So you can see it's the same pattern, 10 bits repeated over time, okay? So now if we take the XOR operation between the original data and the pseudo-random code, right? The code here. If we take the XOR, all right, so let's say this is 1, 1, so we got 0 here. This is 1, 0, so we got 1 here. 1, 1, we have 0, 1, 1, 0, and so on, right? So we take XOR of this, we get this sequence of bits. And this is the sequence of bits that we would transmit over the medium, all right? Again, this is original data 0. So we take XOR of this with this sequence of bits, 0 and 1, we have 1, 0 and 0, we have, sorry, I may have missed it, sorry. Yeah, 0 and 0, sorry, yeah, and we get 0. 0 and 1, we get 1, 0 and 1, we get 1, right? So we do this for every original data bit. So, and this is the new sequence of bits that we will transmit over the medium, okay? So if we compare this with amplitude modulation, you see they're very similar, right? So the signal here is equivalent to the original data, right? And then this is the carrier with much higher frequency, right? Again, the carrier here has higher frequency than the original data. And then we modulate this signal using the carrier. So we get this. In this case, instead of using a special kind of circuit to modulate the two signals, we use the XOR operation, basically another kind of modulation. And we get this sequence of signal to transmit, all right? Okay, so this is one example. Now this is another example, okay? So in this example, we have 3 users and each has its own code, all right? So this is the code here. So this is 1 minus 1 minus 1, 1 minus 1, 1, 1, 1 minus 1 minus 1, 1, 1. So they have different code. You could imagine as if each radio station has its own frequency, right? So this is the frequency belongs to radio station A. This is the frequency belongs to station B. Frequency belongs to station C. And if the 3 radio stations transmit at the same time, because they have different frequencies, there could be no interference, right? Similarly, in CDMA, if different users use different codes, all right, and the codes must be orthogonal. We'll talk about this later. Just like different frequencies must be orthogonal so that the radio station do not interfere with each other. Similarly, the codes here must be orthogonal, and we will define what does that mean by orthogonal in the next slide, all right? So now we assume that the codes are orthogonal, okay? They are orthogonal. So yeah, so again, just to recall the definition of orthogonality. If you have two frequencies and we say that they are orthogonal, what it means is they do not overlap. They are separate frequencies. And because of that, they do not interfere. All right. Similarly, when we talk about orthogonal for the codes, they have the same meaning. Okay, so we'll see later. And in this example, we want to encode the message 1101. Right. And in this example, what we do here is we multiply. We assume that 1 is 1 and 0 is -1, right? If you think about it, when we encode binary digits in a real system, we don't have 0, right? We would have, let's say for 1, it's a positive voltage, and for 0, it's a negative voltage, all right? So 0 could be equivalent to a negative voltage, or we say -1. So in this example, we don't do the XOR, but we multiply the digit, the data, with the code, right? So if we multiply this code with 1, so basically we keep the same form of the code. Again, with 1, we keep the same form. And then if we multiply this with -1, right? Remember, in circuits, we don't have 0 voltage. We will have two different voltages. One for 1 and the other is for 0. So we can assume that we use a positive voltage for 1 and a negative voltage for 0. So if we multiply this by -1, then you can see that these codes will be inverted, right? So that should be now, instead of 1, it becomes -1, and then -1 and -1 become 1, 1. 1 becomes -1, -1 becomes 1, and then 1 becomes -1, all right? So you can see that this is another example of CDMA in which we use a multiplication instead of XOR, okay? And so these would be the sequence of bits corresponding to this message, and it will be transmitted over the air. Similarly, for user B, if we use this code, we get this sequence of bits corresponding to the message 1101. Similarly, for C, the sequence of bits corresponding to 1101 if we use this code, all right? Okay, so now that is the definition of CDMA. Now we go into details and see how CDMA is implemented and how different users can transmit on the same frequency at the same time, and we can still distinguish the data, all right? Now, in this case, after, let's say, 3 of them would send the same message, right? And 3 of them can use their own code to produce their own sequence of bits, and they can transmit at the same time, all right? All 3 of them can transmit at the same time on the same frequency at the same time. All right, so we don't need FDMA, we don't need TDMA. In this case, 3 of them can transmit at the same time. The receiver, to the same receiver, the receiver will be able to separate the signals from each other. All right, the receiver will want to separate the signal from each other and recover the original message from user A, from user B, and from user C. All right, so that's the main idea of CDMA. Basically, each user is given a different code, all right? And the codes are orthogonal to each other. And then each user would use their own code to encode a message. And these messages can be transmitted at the same time on the same frequency. And the receiver, the same receiver, will be able to decode the sequence of bits and get back the original messages. All right, so that's the main idea of CDMA. Okay. All right, so let's go into the math in order to understand CDMA in detail. Now, so we only talk about synchronous CDMA, right? Because it's easy to understand. There's another form of CDMA called asynchronous CDMA. We will not cover that in this course, but of course you can find a lot of books, or even on a Google search would give you the detail about asynchronous CDMA. Okay, all right. So if we talk about synchronous CDMA, synchronous CDMA exploits the mathematical property of orthogonality between vectors representing data strings. All right. So if we have a data string like this, okay, then it can be represented by this vector, right? We separate the bits into different components of a vector. All right. So we use vector in order to explain the math, right? We use vector here to explain the math. But if we implement this in a system, so we would have electronic circuits to do these tasks. So a data string is represented by this, all right? And then vectors can be multiplied by taking their dot product, okay? So we define the dot product now. So given two vectors, U that has two components A and B has two components C and D. If we take the dot product of U times B, then that would be A times C plus B times D. All right. So that's the dot product of a vector U times B. Okay. So that's the definition of dot product. Now, if you have two vectors and we take the dot product of the two vectors and the result is 0, then we say that the two vectors are orthogonal to each other. All right. Sorry, I'm sorry. Okay. Yeah, so that's the definition of orthogonality between vectors. If we take the dot products of two vectors and sorry, and the dot product is 0, then we said that they are orthogonal to each other, right? So now assume, let's say we have one more component here, let's say X and Y, then it should be the same thing. This should be plus X times Y, right? And so on, okay, and so on. And again, if this dot product is 0, then the two vectors are said to be orthogonal to each other, all right? And because of this property, when different senders transmit over the same medium, we can separate the signals to get back the original messages, okay? All right. So in a synchronous CDMA system, each user is given a code orthogonal to the other user's codes to modulate the signal, all right? And when we say a code, what does that mean by a code? Basically, it's a vector that consists of 1 and -1, right? So again, we don't use 0 in this case because we're talking about how to implement in circuits. And in circuits, we should have the two different voltages. Let's say a positive voltage for 1 and a negative voltage for -1. Right. So again, when we talk about code, orthogonal code, a code means a vector consisting of 1 and -1. So an orthogonal codes have a cross correlation equal to 0. When we say a cross relation, what it means is we take the dot product of any two codes, then the dot product is 0. Okay, so the orthogonal code would have cross the dot products equal to 0. And because of this, they do not interfere with each other when we use CDMA, right? So let's consider this as an example. So assume that in this system, we use a chip-in code of 4 bits, all right? We use 4 bits, all right? Now, so if we use 4 bits, then so this should be 1, right? 1, 1, and 1. So it should be 1, 1, -1, right? 0 is -1, -1. Okay. Now, take the dot products of these two vectors. Okay. So if you take the dot product of these two vectors, what would be the result? Okay, so what will be the result here? 0, exactly, right, 0. Okay, so let's try this one here. This is 1, minus 1, minus 1, and this is 1. So let's take the dot product of these two vectors. So what would be the result? Okay, right, so it's 0, right? So if we keep doing this for every pair of code on this page, every pair of code, you see that you could get the dot product 0. So what it means is on these 4 vectors, they are mutually orthogonal to each other, all right? And that's what we need in a CDMA system. Every user must have a code that is orthogonal to the other user's codes, all right? Okay, so. All right, so yeah, so and so in the IS-95 cellular system in the US, this is a 2nd generation cellular networks in the US. 64-bit washed codes are used to encode signal to different users. So basically, each channel, each frequency would have 64 codes, and they are orthogonal to each other. So, and because of this, you can have 64 users working on the same channel, same frequency at the same time. All right. Okay. So that is the definition of orthogonal codes. Now, how do we use orthogonal codes to encode a message? And then how the receiver decodes the messages from different senders, all right? Okay, all right, so this is how the encoding is done. Each user is associated with a different code, as we said before. So basically, each user would be given a code like this, right? And a 1 bit is represented by a positive code, all right? And a 0 bit is represented by a negative code minus B, okay? So what we're saying here is, given a message, we keep the 1 bits as they are. And the 0 bits would be converted to -1, right? Because if we convert it to -1, then we can encode it using -b, right? So assume that we have v equal to 2 digits, b0, b01, b0, b1, and this is the code, 1 and -1, right? So the data, and this is the data transmit, okay? So what we should do now is so basically 1 would be V, right? 0 is -V, 1 is V, 1 is V, all right? And what is V? V is 1 minus 1. So we have 1 minus 1 here, okay, these two. What is -V? -V would be -1 and then 1, right? So that's why we have -1 and 1 here, okay? And then V again, 1 minus 1. And then V again, 1 minus 1. Okay, so basically given this code, and this is the original message, this would be the sequence of bits to be transmitted over the air. Okay, to be transmitted over the air. So the algorithm would be given a sequence of bits, original data, original message, which is a sequence of binary digits. What we do is we keep the 1 bit as they are, and we convert the 0 bit to -1, all right? And then for each of these bits, we multiply it with the code, all right? We multiply 1 with the code, or we multiply -1 with the code. That's how we get the sequence of bit to be transmitted, right? Okay. So again, if the number of components of a code is 2, then we would double the number of bits, right? If it is 4, then we would multiply the number of bits by 4. We would have 16 in this case. If it's 8, then 8 times 4 would be 32 bits to be transmitted. All right. So you see that as the code becomes longer, of course, we would have more bits to transmit, right? That means we would do more computation, would be more work. But the return would be we can accommodate more users, right? So because if we have only 2 bits, let's say the maximum we can accommodate is 4 users. If we have 8 bits, we can accommodate even more users, right? So that is the trade-off, more computation, but we can accommodate, more users, okay? All right, so now we know how to convert original data into the bits, right? So now this is another example, okay? So we go through this example. Now in this example, we have 2 senders, sender 0 and sender 1, okay? Sender 0 and sender 1. And then what we do here is given the code and then the original data of each sender, we will compute the sequence of bits to be transmitted over the air for each sender, all right? Okay, so sender 0 is given the code of 1 minus 1, okay? And sender 1 is given the code 1, 1, all right? Now just take about 30 seconds to verify that code 0 and code 1 are orthogonal. Okay, so you can just say on the chat, type in the chat window whether they are orthogonal or not, because we don't want to do this if they're not orthogonal. Right, so one person say yes. All right. Okay, any objection? All right, okay. All right, so they are orthogonal, right? Because if we take the dot product of code 0 and code 1, we get 0, right? And then this is the original data, the message to be sent by sender 0, and this is the message to be sent by sender 1. All right, so now we have 2 different messages, right? This is 1011 and 0011, okay? All right, so now the first step is we convert the data into convert 0 to -1, right? We said before, because if we want to implement it in a circuit, we cannot have a 0 voltage. We have to convert it to a different voltage. So now we keep 1 and we convert 0 to -1, okay? So you have 1 minus 1, 1, 1, all right. And then we take this converted data, we multiply by the vector, sorry, the code, right? That means we multiply each bit of the data with the code. So 1 times 1 minus 1, we have 1 minus 1, right? Minus 1 times 1 minus 1, we have minus 1, 1. 1 becomes, so we keep the code, 1 times this, we have this, all right? Okay, now let's do the same thing for sender 1. So again, the first step is to convert 0 to -1, right? So we have -1, -1, 1 and 1, okay? And then we take the converted data, multiply each bit with the code, right? So -1, so that way we have -1 here, -1 multiplied by this, -1, -1, 1, 1 multiplied by 1, 1. We have 1, 1 and 1, 1, all right? No, I mean, okay. So if they implement it in a system, all right, they implement it in the system, they use the circuit, then the circuit could be XOR, all right? But we don't care about the actual implementation. It's easier for us to think about this as a multiplication, all right? To answer Shadan's question, yes, in the system, that could be an XOR circuit, but it's harder to remember the XOR circuit, take longer to do the math. So that's why I'm thinking of this as a multiplication of each bit with the code, right? But you're right, it's an XOR, okay? So that's the first thing. The second thing is, you may notice that when we convert the 0 to -1 here, this is how it's implemented using a circuit, all right? It's implemented using a circuit. And why they do this? Because this is for a computer. It is faster than we are doing the conversion of 1 to 1 and then 0 to -1. Okay, this is how the system implemented this kind of conversion. All right, and you can see why it's faster, because it's multiplied the original message by 2, right? And when you multiply something by 2, basically you're shifting the bit to the left by 1 position, right? So the shifting by 1 position is multiplied by 2. And then after you get the new value, you subtract 1, 1, 1, 1. So it's easy to build this circuits, right? Now for us, this would take a long time, right? This would take for us a long time to do this kind of computation, multiply this by 2, and then minus this one. For us, it's easier to understand that we convert 0 to -1, okay? But to let you know how this is done in a circuit, all right? Okay, and the same thing here. It's doing the XOR operation, yes, but it's easier for us to remember and to understand if we take the multiplication of each bit with the code here, all right? Okay, so that is the conversion encoding to convert the original data to a sequence of bits, okay? And then they will, sender 0 and sender 1 will transmit the signal over the air, all right? Now, when they transmit the signal, because they transmit at the same time, we assume that they transmit at the same time. So that means the transmissions are synchronized. So that's why we have the term synchronous CDMA here, okay? That's what it means. So assume that they transmit at the same time. And you can see that if we have 1 and you transmit them at the same time, then we would add the signal together, right? So that means the signal now will become 1 plus -1 is 0. And then -1 plus -1 is -2. -1 plus -1 is -2. 1 plus -1 is 0. 1 plus 1 is 2. -1 plus 1 is 0. 1 plus 1 is 2. -1 plus 1 is 0. Okay, so basically they transmit at the same time synchronously. So we add the signal together. Okay, so that's what we have here. We add them together and we get 0, -2, -2, 0, 2, 2, 0, 1, right? So this is the combined signal transmitted over the air, all right? Now we will see how the receiver, so basically receiver would receive the signal, the combined signal, how the receiver can decode this signal to get back the original messages from sender 0 and sender 1, okay? All right, so now we have the signal and we do the decoding, all right? Okay, and then we have 1 and -1, all right? All right, so the first step we have to do is we have to separate this sequence into subvectors. Now remember, each original bit, right? Each original bit is now represented by 2 coded bits, right? So this one is represented by 1 -1. This 0 represented by -1 and 1. 1 here represented by -1. So what we do here is, yes, we separate this sequence of bits into subvectors. Each has 2 components, and each component corresponds to 1 original bit, all right? So that's why we separate these into 1 subvector, the next subvector, the next subvector, the subvector, all right? So this corresponds to the first bit, this corresponds to the second bit, third bit, and fourth bit in the original data, all right, in original message. And then we do this, we separate them. And now we take the dot product of every subvector and the code, right? We take the dot product of every subvector and the code, okay? So if you take the dot product of 0, -2, and 1, -1, that could be 0 plus 2, right? -2 times -1 is 2, 0 plus 2. We take this subproduct here. So that should be the subvector, the product of subvector and the code could be -2 plus 0. This should be 2 plus 0. This should be 2 plus 0, right? So we would have these, and then we add them. 2, 0 is 2, -2, 2, and 2, all right? Now, when we have the final data here, okay, it doesn't matter the value. When we see a positive number, that means it's a 1. And when we see a negative number, that means it's a 0, all right? Remember we said positive voltage is 1, negative voltage is 0. So basically we convert that into the sequence of data. Positive voltage 1, negative voltage 0, 1 and 1, all right? And that's how the receiver gets back the original message from sender 1, okay? Now if we repeat the same process with sender 1, okay, then you can see that the data that the receiver gets for sender 1 is -2, -2, 2, and 2. So this converted to 0, 0, 1, 1, okay, meaning 0, 0, 1, 1, all right? So, and that's how a receiver can decode the combined signal to get back the original messages from each sender, all right? Now, in this example, we assume that both of them both senders have data to send, and they send them simultaneously, right, at the same time. Now, what if only one sender has data to send only one sender sends data? How can the receiver knows that the other person doesn't send anything, right? So this is that example. So now assume that only sender A sends, sender 0 sends data. So that means this is the transmitted signal, right? This is sender 1 doesn't have anything to send. So this is the transmitted signal, okay? 1, -1, -1, and so on, 1, -1. Okay, so we repeat the same process here, okay? So only sender 0 transmits data signals. So this is a signal. And we repeat the same process, right? Separate this into subvectors and then taking the dot product of each subvector with the code, all right? And we get 2, -2, 2, 2. So this means this is converted into 1, 0, 1, 1. So the receiver repeats the same process with sender 1, right? Using this signal, okay? And the code is 1, 1. So this is the code for sender 1. We do the same thing. Decompose this into subvectors and then taking the dot product of each subvector and the code, right? And if we do this, we get back 0, 0, 0, 0. And this means that there's no data, all right? So that's how the receiver knows that, oh, there's no data from sender 1. Only sender 0 sent the original message, all right? And that's how senders can send data using orthogonal codes using synchronous CDMA. And that's how a receiver can decode a signal to get the original messages back from senders, from different senders, right? Okay, so the benefits of, there are benefits of CDMA technology, okay? It can increase the system capacity by up to 6 to 18 times compared with the analog AMPS system. So AMPS is the first generation cellular network, and it's used analog data, analog signal. CDMA, which is digital signal, can offer 6 to 18 times higher capacity. And it's also simplified the RF engineering, because now we don't need to separate to divide the medium into many frequency bands, right? We need to use only one frequency. That's good, right? We only need one frequency, and all the users can share the same frequency at the same time. Okay. So, and it's also increased performance over the air interface. So the air interface is usually the weakest link in a wireless system, because the air interface has noises, interference, and that's why it's the weakest link. And usually noises, interference, we cannot control it. We can improve the system hardware, the system software, but how can we improve the air interface, right? If there's rain, if there's storm, then that's it. We cannot do anything about it. But with CDMA, we can improve the performance over the air interface. And the way to do this is using something called a REC receivers. So basically a REC receiver is a radio receiver designed to counter the effects of multipath fading, all right? So we're not going into REC receivers in the course. This is more like a hardware problem here. But the purpose of REC receiver is to solve the problem of multipath fading, okay? And then we can only use REC receivers with CDMA, all right? So with CDMA, we can design REC receivers to solve the problem of multipath fading. Sorry. So other benefits could be lower transmitted powers levels. So what it means is that would be lower the electricity bills at the base station, lower energy consumption, and longer battery life for the cell phones, the handsets, right? And it provides greater security because of the encoding of CDMA signal. And it also gives better performance in terms of quality, like voice quality, due to soft handoff operation. Okay. Soft handoff means, so when a cell phone moves from one base station to another, soft handoff means that the connection is maintained throughout the process. There would be no break, no disconnection during that process. So that called soft handoff. With hard handoff, what it means is there may be a short interval when the connection is disconnected, but because the interval is so small, users may not notice it, right? But in any case, soft handoff is much better because there's no interruption during the handoff process. Okay. All right. So there's a question from Joshua. Each user having a different code allow multiple users in the same frequency band. Yes, that's right. Okay. So each user is given a different code. And let's say we talked about before in the IS65 system, right? In IS65 networks, we used 64 bits codes, right? And 64 codes here is orthogonal to all others. And the signal, now we could have 64 orthogonal signal at the same time, all right? Exactly, and they wouldn't cause interference if they transmit simultaneously, exactly. Okay, so if each user has a different code, they can encode their signal, all right? And they would not interfere with each other. And we can see from this example here, this is the encoding, and this is decoding, all right? And they can get back the original signal, okay? The set receiver can get back original signal, all right? Okay, any more question about CDMA? All right, so one thing we have to keep in mind that the codes must be orthogonal, all right? In order to avoid interference, the codes must be orthogonal to each other, all right? And orthogonal means their dot product must be 0, okay? The dot product must be 0. All right, so if there's no question, then we can do the test, sorry, the quiz, and then we take a break, and then we come back and continue with 2G networks, okay? All right, so let me enable the tests on eClass, the quiz, sorry, the quiz, I keep saying the test. Okay, so let's see here, okay. All right, so if you go to the end of the page and refresh your eGlass page, you will see quiz number 6. Okay, so I will type the password on the chat window. Okay. Okay, so I will show the password. Okay, 1 second. All right, so the password is security 3103, right? So good luck. Okay, so let's continue with the 2G networks. Okay, 1 second, let me check. All right, so so last time we started the GSM network architecture, right? So GSM is the second generation cellular networks, and we talk about 4 components of a GSM networks. We have a base station subsystem. All right, so this part here, we have a network subsystem. This part here, the second block here, and then we have the operations and support system, this small box here, and then the mobile station subsystem, basically the mobile phones, right? And we went over the first block, which is the base station subsystem. Now we continue with the second block. Right, so now we talk about the network subsystem. All right, so basically this block right here. Okay, so this block has many components. One component is the mobile switching center. So you can consider this as the computer, the processor of this block here, right? It's a computer. So the BSC, the base station controller, you can consider them as the computers for the this block here. And the OSS, the operation and support system, you can consider this as the brain of the network, right? So this is like the brain, and this is another function, like nervous function. Let's say you consider this as the spine, for example. It has all the nervous function. So this is the brain of the system. Let's say this is the spine of the system of a human body, for example. And then in this network subsystem, there are many components. And the purpose of the network subsystem is basically, it has many purposes. It's provide mobile registration, location updating, authentication, call routing, and other security function, for example, right? So now we go through each component in this system. So this is the message switching center. Basically, it's considered as the computer of this block. We have the home location register. So this is a database that contains information of the user in the cellular networks, basically the subscribers of this cellular carrier system. And then we have another database called the visitor location register. So it contains information of visitors. So when someone from another carrier roams into this network, so this database will contain the information of that visitor. And then we have a authentication center. All right, so by the name indicates that it uses for authentication and also for security purposes, for encryption purposes. And the authentication center uses another database, which is called the equipment identity register. The equipment identity register is a database used for security purposes, and it contains the records of all the mobile phones. Basically, the mobile phones from the home location register or the visitor location register, these the mobile phone for these users. And in a GSM network, there are 3 kinds of phone. One is a black phones. Basically, these are phones that should be banned from the network. For example, a phone is stolen. The second type is white. Basically, white phones are valid phones, so they should be used in the network. They can be used in the network. And the third one is gray phones. So gray phone means they are not sure about these phones. These gray phones may still be used in the network, but they will need to do more investigation to determine whether it's black or white, right? So that is the equipment identity register. And then when we talk about the equipment identity register, there's something we need to talk about, which is the International Mobile Equipment Identity, IMEI. So when a mobile phone requests service from a network, its IMEI is checked against the equipment identity register, this database, to determine the category to which the mobile phone belongs, to determine whether it's a black phone, a white phone, or a gray phone. And every GSM phone manufacturer would give a unique identification number to every phone, and that number is called the IMEI. And the IMEI is a unique 15-character number for every valid phone that a GSM network uses to identify a mobile phone. Okay, and the IMEI numbers are assigned in the factory. And if a user phone gets stolen, then he or she can tell the carrier, and the carrier would block that phone using the IMEI, making it useless to be used in that network. So, so in theory, every cell phone should have a unique IMEI, right? So that's why no two cell phones will have the same original numbers. And but in practice, the numbers can be changed, right? So if someone stole a phone and then changed IMEI, that can be changed with special software and a unique cable, all right? And new numbers can be programmed into stolen phones. So in the past survey or past statistics, the British Cellnet carriers say that about 10% of the IMEIs in their network were not unique. All right, so this is from UK, this is the data from UK. So basically these phones were stolen, and then they changed the IMEI to another number of white phone or valid phone. Okay, all right. Now, if you're curious, you can see the IMEI number of your phone by dialing the sequence on your phone, and you will see it. Okay. And again, if an IMEI number has been stolen, then that IMEI will be placed on the blacklist in the equipment identity register, and it will not work on the network. So in that case, the thief would have to reprogram the IMEI number in that phone in order to reuse the phone. So that's why we can have duplicate IMEIs in the network. Okay. All right, so that is the subsystem here, all right? The network subsystem. Now we're talking about the OSS. So the OSS, the Operation and Support System, is a command center that is responsible for monitoring and controlling the whole network, all right? So that's why we consider it as the brain of the network. So if there's a major outage happening at a base station, then the OSS can locate that problematic base station, and then it can determine what type of failure has occurred and what kind of equipment that an engineer needs in order to repair the failure, right? It has that kind of information. So this is the OSS. So again, it's considered as the brain of the system. It monitors and it controls the whole network. Okay. So, and then of course, the mobile switching center of this network or this carrier can be connected to another mobile center of the same carrier or another mobile center of another carrier or the same carrier, right? And then we have something we call a gateway mobile switching center. So basically, this is the gateway between this network and other kind of networks. And we see when we say other networks, it means it doesn't have to be a cellular network. It can be, let's say, to a router, to the internet for data, not for voice, but for data, for example. Okay. All right. So we cover 1, 2, 3 on 3 blocks. So the last component, the last block is the mobile station subsystem. Okay. So the mobile station subsystem will contain, of course, the phone itself, and then the second component is the SIM card. Okay. So of course, the phone in a GSM network is different from analog phones because they are digital. And the identification information of the subscriber is programmed into the SIM card, the SIM module, and not the phone itself. And again, for portability, right? So you can use the same phone with different carriers, so that you can use the same phone with different carriers. And and again, I know that you know what a SIM card means. It's basically a microcontroller, and it holds the GSM operating program and the customer data, the carrier specific data, and the information of the subscriber. That's why every time you change to another carrier, you need to change the SIM card on your phone, right, in your phone. And the SIM card provides authentication, provides information storage, subscriber account information, data encryption, and so on. It has several functions. Okay, right. So again, GSM authentication is much more advanced than in analog networks. And today, there's been no cloning fraud on GSM system due to the authentication technology that is more advanced than in an analog system. And then with GSM, what we have is a soft handoff, and it's also mobile assisted handoff. What it means is the mobile phone plays an active role in the handoff process. So in the analog system, the switch is responsible for finding a good base station for the mobile phone to move to. In GSM, the mobile phone will monitor different base stations around it, and then it measures the signal strength of these base stations. And then it will identify the 6 best base stations. And then it sends the identity of these 6 best base stations to the switch. And then the switch will then decide when to initiate a handover and to which station based on the information sent by the mobile phone. All right. And you can see this is good in the sense that now the decision is done in a distributed manner. That means every mobile phone is responsible for finding the best base station. So the switch doesn't have to do it. So it will speed up the processing, the computing at the switches, right? So now it gives this task to the mobile phones. And then the mobile phones, again, are in the best position to determine the best base station based on the signal strength that it measures from adjacent, from nearby base stations. Okay. All right. So now, so far, we've been talking about the architecture of GSM, but we only talk about the voice component, basically voice component of GSM networks. Okay, so now we move to the second part of GSM network is how it handles data, right? So voice and data, how does it handle data? So the architecture we're talking here, they are for voice. All right, so now we'll talk about data. So before we go into that, there are some other action systems in a GSM network. That means other blocks, other entities in a GSM network. So the first component is called a gateway mobile switching center. Okay, gateway mobile switching center. So the the purpose of the gateway MSC is to connect this network with other networks. So that's why it has the term gateway, all right? So specifically what it does is to query the home location register to determine the location of subscriber. So that's one function. And then call from the other networks will arrive here first before it is sent to this network, all right? And the other way around, if a phone call from this network want to be sent to other networks, have to go through the gateway MSC. So that's why we have the term gateway there, because it's the interface between this network and other networks. And there's another entity which is called short message service center, SMS service center, used for processing text messages. All right. So if we so basically in this diagram there should be a another component which is for text messaging. All right. So maybe we'll talk about that later for text messaging. All right. But remember, there's another service called SMS for text messaging. And then we have something called gateway GPRS support node and service GPRS support node. Okay. So again, GPRS is it's called general packet radio service. So it is a another service on top of a GSM network in order to handle data, basically handle packet traffic, right? Not voice. This is data. Okay. So now we'll talk about GPRS, and then we will see where the gateway GPRS support nodes and where the service GPRS support nodes are, where they are located, and what will they do. Okay, what can they do for the network? All right. So now the GSM, this network here, is only for voice, right? This is for voice only. Now, if we need to support data, when we say data, we mean text messages, to browse the internet, for example, to send email if through your phone. So that will be data services. If we want to do those things, GSM network needs extra another layer. And the first version of that layer is called the General Packet Radio Service, GPRS. And it was an overlay network on top of the existing GSM network. And it provided data rates from around 9.6 to 171 kilobits per second. And multiple users can share the same air surface resources. Now, GPRS is not in use anymore in GSM network these days. Exactly, GPRS would not be used anymore. GPRS is in 2G networks. Okay, so right now we don't use GPRS anymore. Right now, if there's still 2G networks existing, but I don't think there are now, then GPRS has been replaced by EDGE, right? EDGE stands for Enhanced Data Rates for Global Evolution. So we'll see these two technology later. But Shadan, you are right. So these days we don't have GPRS anymore. We have LTE, which is LTE Advanced, which is 4G or 5G, right? And if we still have 3G networks, there's still maybe 3G network, that would be UTMS, okay? Right. All right, so and then CDMA, we just learned in the first half of the lecture, that would be in some part of the 2G networks, and for sure they are in 3G networks, okay? All right, so now we'll talk about GPRS, and then we talk about EDGE, right? So GPRS, again, they're not used anymore in GSM networks, but it's good to know GPRS because EDGE is built upon GPRS. All right, so so basically GPRS is called 2.5G, right? Because it's an enhancement on top of the GSM network. So it's implemented a packet switch domain in addition to the circuit switch domain that existed in GSM network. And theoretically, it can provide a maximum speed of 171 kilobits per second if all the GSM time slot were used at the same time, right? Remember we said about GSM, we use TDMA to divide each frequency into 8 time slots, right? So now this is a diagram of a GSM network with GPRS, right? Now, my first question, do you know the definition of circuit switching and packet switching? All right, before about packet switch, circuit switching. Do you know the definition of circuit switching? Just a yes or no on the chat window. Right, Joshua said it's a physical method. Yes, you're right. Okay. Okay. Right. Okay. So it just with physical wires. It can be used wireless in a wireless environment as well. Okay. But all right. Any other answer? All right. With circuit switching. All right. So now you know how the internet works, right? If you took 3313, you know how the internet works. When we send a document, a large email or a web page, the document is cut into packets, right? And the packets each packet is sent from one router to the next. And at each router, the router determines the next router to forward the packet to, right? So basically that is a packet switch network in the sense that the next hop is determined by the current router based on some routing algorithm, all right? So at every router, the packet is switched to another router. So that's why we have the term packet switch there. And that the next hop is determined by a routing algorithm, okay? So that packet switching, so that means there's no path reserved in advance for a packet, all right, or for a document, for a connection. Now circuit switching, so circuit switching is used or was used in the original telephone network. So when a person places a call to another person, a circuit or a path is reserved from the caller to the callee, right? To the between the two people. Basically, the whole circuit or the whole path is reserved. All right. There's no switching. No packet to switch at each router. If there are routers on the way, or we call switches on the way, though the whole path is reserved in advance, right? The whole path is reserved in advance. And that path is called a circuit. So that's why we call this circuit switching. So that means the sender will send a signal to the receiver. I'm talking about receiver, but basically there are two people talking to each other. A signal is sent from the sender to receiver, and then the whole path would be reserved for that call, right? And the whole path is reserved for the whole duration of the call, right? So you can see that circuit switching is used in the original telephone network, and it's also used in, so that's why it's this part here, the public switch telephone network, all right? So that's why it's applied to the voice component of GSM network. It still uses circuit switching, all right? So now you understand the main concept of circuit switching. Basically, the whole path is reserved, right? For a call. So of course, the The disadvantage, the advantage is the delay is very low because the whole path is reserved. The disadvantage is that you may be wasting bandwidth, right? So if let's say there are many silent period between the two people conversing, but the whole circuit is occupied for the whole conversation, even though they may not say anything to each other. All right. So you can see that it's a waste of network bandwidth. But that was the early technology that we had in order to build a telephone network. And later, when we have data services, when we have more advanced technology, then packet switching is was created, right? So the first part here, the circuit switching part, is handles voice, right? Like telephone calls. And you remember that this is the MSC we said about before. Basically, it's this part here, all right? This block here, right? But now they simplify it into this part, right? Only a small block like this, and this is connected to the public switch telephone network, and this network uses circuit switching. So the whole part here is using circuit switching. Now in GSM network, we have data. So that's why they created a separate network based on the packet switching technology, all right? And this is called the GPRS core. Basically, it's a different network from this based on packet switching. And then the two components we said about before, the serving support node GPRS and the gateway support node, right? So of course the gateway support node is connected to the internet by its name, right? Gateway. And then the serving node is connected to the base station, right? The base station controller. So that if someone from the internet send a text message to someone in the network, it will be sent through this network, packet switch network, to the base station controller, to the base station, to the phone, or to the laptop, all right? And within here, we have an IP network. So basically a set of routers, right, to route packets from the internet to the base station, or the other way around, from the base station to the internet, okay? All right, so this is the GPRS network architecture. Yes, and we said before GPRS, existing mobile telephone switching office were designed for circuit switching traffic, and they could not process packetized traffic, right? So that's now we need a GPRS network, and it could have these two nodes here, all right? All right, so let's talk about the serving support node first, okay? So the SGSN. So again, it's performed the mobility management functions such as mobile subscriber attach and detach and location management. Basically, it's performed similar tasks as the MSC, but for data. And it is connected to the base station system subsystem here through a unit called packet control unit. All right, so we'll see that in the next diagram. And it handles all the packet switch data within the GSM network. So it handles data. And then it performs the same function as the mobile telephone switching office of the same function. The MTSO, the mobile telephone switching office, is for voice. So the SGSN is for data. And the SGSN is connected to the base station controller, one base station controller, or several base station controller. And this is the service access point to the GPRS network for mobile user. So basically, this is the access point from the user to this packet switch network. Okay. All right. So now from this is like a high level architecture of a GSM network with two components, the voice component and the packet, the data component, right? Now, if we go into a more detailed more detailed diagram. So you can see we have two parts, one on the left and one on the right. The left is the voice component, right? The voice component. We have a mobile switching center here, all right? And then we have the gateway mobile switching center. And this gateway, so the gateway MSC is connected to the public switch telephone network. And this part handles voice messages, right? These part handle voice phone calls, okay, this part. And then on the right side, we have the second component that handles the data, right? So basically, this now becomes the left part, and this is the right part, right? The right side, the left side, the right side. And this handle data, packetized data. So we have the SGSN, the serving support node. Sorry. So please excuse me just for about 1 minute. Yeah. All right. Sorry, I had to get some water. Okay, so let's continue. So the second part here handles the packetized data, right? And you can see that the MSC now has an equivalent counterpart, which is the SGSN. And then the gateway MSC, now we have the gateway GSN, right? And then both of them are connected to the home location register and the equipment identity register, because both of them need to access these databases, right? Sorry, and the authentication center needs access to these as well. All right. And then now this is the PCU, the packet control unit. So the packet control unit so the packet control unit is a separate hardware element associated with a base station controller. Sorry. Okay, sorry about that. So the PCU decides whether the data to be routed to the voice component or to the data component, right? So let's say if the base station receives a text message, so the text message will go through the controller, and then the PCU will decide that the text message should be forwarded to the data component, right? If it is a phone call, then it will decide that it will go to the voice component of the network, right? So that's the purpose of the PCU. Now let's talk about the, let me see here. Yeah, the SGSN. So the SGSN is equivalent to the MSC, right? The mobile switching center. And we talked about this before. This is the access point between mobile user and the GPRS network. Now the gateway GPS support node GGSN. So this is an interface to the external IP network, the internet. And it's connected to other, of course, other GPS network in order to facilitate roaming of a mobile phone from one network to another. And it maintains routing information because in the network here, sorry, where is it? Yeah, in this diagram here, there should be some routing to be done here, right? Be done in this way, and routing to be done from here to the internet. So this is the function of the GTSN, okay, to do the routing. Okay, so, and all right, so this is the PCU. Now, in addition to these components, the GTSN, FGSN, and the PCU, we need other nodes to implement GPRS service. So we'll talk about PCU already. That's on another module called to do mobility management, right? So that it can locate the mobile stations in the network. There would be a new air interface for packet traffic. When we say air interface here, that means a new kind of modulation, a new kind of signal for data, different from the voice, from voice signals. There would be new security features as well for data, and a new GPS specific signaling system as well, because it's for data, it's different from voice. And then we will need some modification in the base station subsystem itself in order to support data traffic. So basically both voice and data will use the same base station controllers and use the same base station, just like before, right? So basically here, yeah, they will use the same base station controller and base station. The only thing we need to change here is at the output port of a controller, the traffic was separated, right? The voice traffic will be sent, sorry. Right, so the difference here is at this point here, the voice traffic will be sent to the MSC and the data traffic will be sent to the FGSN, okay? So that's how the base station had to be modified to support data traffic. Okay. All right. So that is the GPRS architecture, right, and different components. Now, GPRS was later replaced by something called EDGE. All right. So EDGE stands for Enhanced Data GSM Environment. Sometimes EDGE is called Enhanced GPRS. Why? Because it's built upon GPRS, right? So you can consider you have a GFN network with voice. We add a data component, which is GPRS, and then we enhanced that GPRS component, and we have EDGE. So that's why EDGE, also known as 2.75G technology. Okay. Now, but now these days there's no more. There are not many 2G networks. So usually it's used as a fallback option where 3G networks cannot be implemented. And then again, EDGE is introduced into the existing GSM and GPRS network rather than creating a new one, right? So now GPRS was a new component added to a GSM networks, but EDGE was built upon GPRS. Okay, so don't forget that EDGE was built upon GPRS. All right. And why did people create EDGE? Again, just to have higher data rates. So each GPRS time slot can handle a maximum of 20 kilobits per second of user data, right? And then user data. And then if we add some overhead for packets, we have about 22 kilobits per second. All right. And then if we combine all of these together, we have a peak rate of about 172 kilobits per second on 8 of them are used simultaneously. Edge, Edge can squeeze more data into each time slot. All right. A single Edge time slot can handle up to 59.2 kilobits per second. So about 3 times more than GPRS for a total of 473.6 kilobits per second, about 3 times of this number when all 8 time slots are in use. Okay. And how can Edge offers higher data rates? Okay. It uses a better encoding, new in channel encoding, a better modulation technique. Okay. So Edge introduces a new modulation technique. We'll see in the next slide, a new channel encoding, right? So again, Edge is an add-on to GPRS, and a carrier cannot deploy Edge unless they already have GPRS in the network, right? So basically, GPRS is the foundation, and then now GPRS is supported only very low rate. So now we want to improve the modulation technique. So we can use the same architecture, but we just change the hardware to support new modulation technique. And in that way, we can increase the data rate, right? And let's see how Edge can improve the data rate here. All right, so GPRS uses something called Gaussian minimum shift keying, all right? So basically what this means, it is a form of continuous phase frequency shift gain, right? So the keyword is frequency shift gain. So you can see bit 1 is represented by this frequency, right? Bit 0 represented by a different frequency. So basically you have 2 signals here instead of 1. And then for 1, it's 1 signal, 1 is 1 signal, and 0 is 2 signals, right? So you change the frequency. You have 2 different frequencies, and each frequency represents a 1 or 0. So that is GPRS. It uses frequency shift keying. And Edge uses 8-phase shift keying. All right. And this is 8-phase shift keying. So you see, if you use 8 phases, then each phase can represent 3 bits, right? So in this example show here the 3 bits, right? And then you have the signal. Then for 001, you change to a different phase, 010, a different phase, right? And so on, by using 8 phases. Now each signal can represent 3 bits instead of 1, right? So you see in this case, a signal can represent only 1 bit, right? A signal 1 bit. Here, a signal can represent 3 bits, right? 3 bits. So that's why you can see when we talk about the rate before, Edge can provide 3 times higher data rates, right? Because of this, a signal can now represent 3 bits instead of only 1 bit, okay? All right. And this is the comparison in terms of data rates, okay? Sorry. So I need to charge my laptop. And if we take a look at these numbers, you can see that the modulation for GPRS is Gaussian minimum shift gain or frequency shift gain, and this is 8-phase shift gain. The modulation rate is 270 kilobit per second. This one is 810. You see about 3 times. Radio data rate per time slot. Again, this is about 3 times of GPRS, right? Edge is about 3 times higher. And if we subtract the packet headers, we keep only the user data rate. This is about 20 kilobits per second. This is about almost 60 kilobits per second, 3 times. and the user data rate in on time slot. We take this multiplied by 8, and we get 160. This multiplied by 8, we get 473.6. So this one is about 3 times higher than this. All right. So these numbers support our support the ideas that we use a phase shift key and we can encode 3 times more data per signal. That's why we get 3 times higher data rates. Okay. All right. So if we talk about the technical differences between GPRS and EDGE, they have different protocols, right? They have different behavior on the base station system. And it makes sense because they use different encoding scheme, they use different modulation techniques, so they should have different behavior on the base station system side. However, once the packets are routed in a network, GPRS and EDGE share the same packet handling protocol on the core network side, right? Because again, packets now are a sequence of 0 and 1. They will be routed through the network the same way. So EDGE has higher capacity, right? So the same GSM time slot can support more user with EDGE, basically exactly 3 times, right? Because it has 3 times higher data rate. Okay, right. So so in order to implement EDGE, what did we need to modify in order to implement EDGE? So of course the base station was affected, right? Because now we need a different transceiver unit to handle 8 phase shift keying instead of Gaussian minimum shift keying. However, the core network does not require any modification, right? Because they only handle packets. There's no transmission over the air. And because of that, the EDGE technology could be deployed with limited investment and within a short time frame, because we only need to add or to replace the new hardware at the base station to handle the new modulation technique instead of using GMSK. Right? All right, so and then we talk about CDMA technology. So basically GSM and CDMA, they were created at the same time, right? So if we take a look at this chart here, so GSM is here, right? 2G. So at the same time, and then we have EDGE here, right? 2.75G or 2.5G. At the same time, in the US, they have a new system called IS, Interim Standard 95. And this uses CDMA, right? GSM is TDMA, but IS 95 is CDMA. So basically, these two coexisted at the same time as 2G network. This is in the work. This was created in Europe. This was created in the US. Some carrier in the US also use GSM, right? But these were created at the same time. And then at that time, before they moved to 3G, there was debate about which technology is better, GSM or CDMA, all right? And at the end of the day, the conclusion is that each has its own benefits and disadvantages. So that's why the 3G based technologies take advantage of the best aspect of both technologies. All right, so in 3G networks, so that's why in 3G networks they use CDMA, but at the same time they adopted many good aspects of GSM as well. Okay, and 3G network is the topic we'll talk about next week in the next lecture. Okay. All right, so that's the end of this lecture. This lecture is from chapter 7 in this textbook. Again, it's in the library on reserve. There may be an online copy of a second edition on the internet. Okay, and when we talk about CDMA earlier, let me open the CDMA slides again. When we talk about CDMA earlier, the material is from this textbook by William Stallings, chapter 9. And then the examples the examples were taken from this Wikipedia page, right? So if you want more, you want to read more about the example here, you can go to this Wikipedia page for the example, right? Okay. All right, so that's the end of this lecture. Thank you everyone for participating. If you have any question, I will stay in the next 5 minutes to answer your question. Otherwise, have a nice weekend and I'll see you next week. All right. Okay. Okay, Samyak has a question. Is there a quiz in the next class? Yes, there will be a quiz in the next class. The next class, there will be one more chapter. Okay, there will be one more chapter. So if there's a quiz in the next class, that would be on 2G networks, right? On 2G networks. Basically from this set of lecture, the new set of lecture. And CDMA as well. Sorry, I forgot about CDMA. Okay, CDMA. Let me see tomorrow. Tomorrow, my office hour will be on Zoom. Yeah, tomorrow it will be on Zoom. Yes, so. So to answer Ruchi's question regarding the market return, yeah, so you can attend the office hour tomorrow, and then I can go over the paper with you. All right. Yeah, I mean sometimes TA may make mistake, for example, or they may, let's say in the past year, sometimes they skip one question by accident. So if there's any issue with the midterm, please come and see me in my office hour tomorrow, and I will answer your question. All right. Yeah. Yes, you can discuss with Honda as well. Yes, you can. But I guess if you want a second opinion, then come and see me. All right. You're welcome. To answer Samyak's question, the panel exam will cover everything or more focus on later chapters. No, the panel exam will cover everything from the beginning up to the last lecture. Right, and I would say with the same percentage, yeah, same ratio. All right, you're welcome.